So hello everyone, I'm Thibault Simonetto, and today I'm going to present you a unified framework for adversarial attacks and defense in constraint feature space, a work conducted at the University of Luxembourg by my colleagues and I. A common way to evaluate the robustness of ML models is to generate adversarial examples. These are inputs that are carefully perturbed such that they are misclassified by an ML model while being imperceptible to human. In many domains, ML is integrated in a larger software system that takes as input domain objects. For a credit scoring system, the domain object is the client's history and an incoming credit transaction. We create feature vectors from the domain inputs to fit them to an ML model. This domain object respects some natural condition to be valid, and that translates to a set of constraints omega over the feature space X. An interesting type of constraint is that some features are linked to each other. For example, the number of open accounts should be lower than the number of total accounts. Similarly, the installment, the loan, the interest rate, and the terms are linked by this formula. Every feature space example must satisfy the set of constraints to be valid. Traditional attacks from computer vision fails at generating constraint examples. The objective of this attack is to produce a perturbation, delta, that misclassifies the example, and minimize the perturbability by bounding the distance between the clean examples and the adversarial one. On the left, you can see the path taken by a iterative attack that at each step increase the loss of the example. However, such attacks that only consider the loss of the model produce examples that do not satisfy the constraints. This is represented as a red region on the picture. The objective is to prevent these attacks from reaching this red region, for instance, by forcing them to follow a path such as the yellow one. Doing so, we would generate adversarial examples that satisfies the constraints. We tackle this problem with a generic framework for adversarial attacks under domain constraints. We first define a generic constraint language to capture the domain constraints, and then we instantiate this framework with two attacks, CPGD and Moeva2. The first step of our framework is to define a constraint language. A constraint omega can be defined as the disjunction or the conjunction of two other constraints. It can be a comparison between two values, and a value can be a constant, the value of features, or the result of the mathematical operator applied to a pair of values. Then we express this constraint as a penalty function using a mapping. We obtain a function that is always positive and evaluate to 0 when the input x respects the constraint omega. Thanks to this constraint language, we are able to handle a large diversity of constraints to instantiate the attacks in different domains. So let's see what our approach. Our first approach to generate adversarial example is an extension of PGD. PGD is an iterative approach. At each step, it adds a small perturbation in the direction of the gradient of the loss function, such that the loss augments, and eventually this leads to a misclassification. For CPGD, we simply include the penalty function of our constraints in PGD. We obtain CPGD that iteratively augments the loss of the model and minimizes the constraints penalty function. Our second approach is a multi-objective genetic algorithm with three objectives. First, the minimization of the probability of the correct class output by the model. Second, the minimization of the distance to the original example. And third, the minimization of the constraints penalty function. So how effective our approach at generating adversarial examples? We evaluate the success rate of the attacks on neural networks and random forest and on 4 datasets: LCLD for credit scoring, a botnet classifier, a malware classifier, and a URL classifier. We evaluate 4 attacks, PGD and Peppernode, that are unaware of domain constraints, and 2 attacks that we presented, CPGD and Moeva. We are interested in the ratio of generated examples that both satisfy the domain constraints and are misclassified. First, attacks that are unaware of domain constraints mostly fail with a success rate of 0%. CPGD is effective on a single dataset with a success rate of about 9%. And Moeva outperforms the other approach and succeeds on every single setting with a success rate from 5 to 100%. So now that we show that our models are vulnerable to such attacks, how can we improve the robustness of our machine learning models? We hypothesize that augmenting omega with a set of engineered constraints can robustify the model. So we add a new feature, FE, that is the XOR between feature 1 and feature 2, and FE, F1, F2 are all used to train the model. We obtain new constraints, omega, following the definition of Fe that must be satisfied by every examples, including the adversarial one that we generate. This hardened the search for adversarial examples. We evaluate this approach and adversarial retrainings and found that constraint augmentation is an effective defense against constraint adversarial attacks, and that, compared to their separate application, the combination of both defenses can decrease the attack success rates by up to an additional 5%. So in conclusion, we propose a generic constraint language to define constraint in a large variety of domains, 2 constraint attacks that we evaluated on 4 datasets, and finally, a novel defense method as effective as adversarial retraining. So thank you for watching, and don't hesitate to check out our paper and the source by following the QR code.